Well, hello and welcome to all our alumni participating in this alumni festival in the new normal online format. My name's Colm Caulfield. I'm the head of department of applied maths and theoretical physics, and I'm also associated with the BP Institute here at the University of Cambridge. This is the first talk of the alumni festival, where there's a wide range of different interesting talks from various people associated with the university, and we apparently have over 27,000 registrations. So it's very exciting to have you all here, and we'd like to welcome you, and I hope you find this session and all the other sessions that you've signed up for interesting. Just some technical notes at the beginning. At the start, your microphones and cameras will be turned off throughout, but there is a Q&A option, and I really hope that my talk will spur various questions, and I'll be very keen to try and answer them, as many as possible, at the end of my talk. And without further ado, I guess I should just start my talk about turbulent heat transport in the ocean, and this slightly provocative question: do we even know what we don't know about that particular process? And of course, I should also acknowledge the various funding agencies associated with this. Much of the work has been supported by either the Natural Environment Research Council of UKRI, the Engineering and Physical Sciences Research Council of UKRI, it's really a multidisciplinary type activity, and also the Cambridge Trust. So, just before I start actually talking about my work, I thought it would be a very appropriate time just to tell you a little bit about mathematics at the University of Cambridge. This is a picture of the Centre for Mathematical Sciences, which has been open about 15 years now. I am actually sitting in an office towards the back, just maybe you can see my pointer. It is there, and you can see behind me the classic accoutrements of a Cambridge academic, a bike jacket and a gown hanging ready to be used appropriately. So mathematics at the University of Cambridge is a very large activity with two departments. I'm in the Department of Applied Mathematics and Theoretical Physics, and there's also the Department of Pure Mathematics and Mathematical Statistics. And together there's about 500 research mathematicians working in these two departments at any one time. I almost said here, but of course, at the moment, they're not exactly here. There's been a lot of wide range of different interests. Of course, with Stephen Hawking's heritage, there's long-standing interest in general relativity, cosmology, theoretical physics, but a broad range of mathematical activities from the purest end to the most applied. And really what I'll be talking about is at the boundary between computational partial differential equations, fluid mechanics, and applications to geophysics, of course, the oceans. And I'd like to just briefly highlight too, much of our activity now is associated in a very broad sense with understanding data. The mathematics of data is really a key part of what we're doing, and I hope to explain that further through my talk. And so also, of course, academic research is a very collaborative activity, and I just thought I'd like to just show you the kind of thing I'm talking about, how much of an international and multidisciplinary activity it really is. Really, the work I'm going to be telling you about, I've been working on for the last couple of decades, and involves 80 people from 20 different nationalities, and with a wide range of first name letters of their surnames. I've worked with 23 different. I'm missing a Q, U, and an X surname, but apart from that, I published papers with all the others. And in particular today, I'm going to be highlighting for you the work of 4 PhD students I've had the good fortune to work with in Cambridge: Kathy Gunn, Chris Howland, Rosie Oglethorpe, and Kanwar Naim Singh. So, what are we interested in? We're interested in understanding the Earth's oceans, and understanding how heat is transported in the Earth's oceans is central to understanding how the climate is changing. Global weather and climate is entirely reasonable to say it is controlled by the world's oceans. This is an amazing data set called OSCAR from Earth and Space Research in Seattle, led by Kathleen Doan and sponsored by NASA. And what you're seeing here is surface currents in the ocean constructed using satellite altimetry data. And you perhaps, we all have heard about this Gulf Stream up the east coast of the United States that fires off towards us in the North Atlantic, but there's also the similar boundary current on the Kuroshio here off Japan, and there's the Agulhas current down off South Africa, and you'll see a very interesting phenomenon that's happening called the retroflexion. You see it's kind of turned back, and that is because the Southern Ocean acts as an amazing flywheel of flow around the world that is that's the one ocean that connects the various aspects, and we'll be talking a bit more about the Southern Ocean right at the very end. So that you can see there's this very, very dynamic weather patterns going on in the world's oceans, and they are strongly affected by three fundamental characteristics. The first is you can see these currents down the middle, i.e. at the equator. The fact that the Earth is rotating is a key dominating physical process that's important in the world's oceans. The second thing that's really important in the world's oceans to appreciate is just how thin a layer it is. So the Pacific Ocean, which in this projection is sort of on the side, is to good approximation is about 15,000 kilometers in this direction, 20,000 kilometers in that direction, and about 5 to 10 kilometers deep. Now 5 to 10 kilometers sounds deep, but that aspect ratio is about 3,000 to 1, which is the aspect ratio of the thickness of a sheet of A4 paper to its length. So it's important to appreciate that the ocean is effectively a very thin film of water. But it is also very important to appreciate that that thin film of water is stratified. It is more dense lower down than it is higher up. And some of that is naturally associated with the fact that the sun hits the top and heats it up, but it's more complicated than that. And understanding the more complicated than that-ness is the fundamental question I'm interested in. Now, as the world's oceans get, as the climate change, the greenhouse gas because of carbon emissions and the climate is modified by carbon dioxide, methane, and so on from agriculture and deforestation, the atmosphere is heating up. But it's much more, it is very important to appreciate that the oceans are heating up too. There is a vast increase in the heat content of the oceans, and understanding the heat content of the oceans determines the global weather patterns and also these circulations that really affect how we live. And understanding how heat moves in the oceans is critical because there is a much bigger heat capacity of water than air. Something we all appreciate, you know, how long it takes to boil a kettle, right? So it's really telling. The Earth's atmosphere is defined as really being the column of air above the surface that goes up 100 kilometers. Now, to heat up that column by 1 degree requires the same amount of heat to heat up the top 3.4 meters of the ocean. The heat capacity of the ocean is vastly larger. And so understanding how heat is transported in the ocean is critically important to being able to understand these ocean currents that you see. And this picture here from a paper, Trenberth 1994, shows just the sort of amounts of heat that's going on. The transport is in petawatts, 10 to the 15 watts, 10 to the 12 kilowatts, but it's kind of funny to describe it in that particular way. Enormous amount of heat is transported from the equator on average towards the poles because of the fact that more sunlight, more solar radiation comes in at the equator than at the poles. And the global circulation of water that we see is, to leading order, there is deep water because it's cold formed near Greenland, around the Southern Ocean, that's sort of shown here blue, and then there are various currents that follow different return cycles. The conveyor belt is a simple way to describe it. That moves the heat around in the oceans and leads to the oceans being stratified. But if there wasn't turbulent mixing, which is shown with this red arrow here, if there wasn't turbulent mixing between the various parts of the ocean, what we would have would just be a stagnant layer of very cold, warm water at the top and cold water at the bottom. The fact that we're seeing these large circulations and the fact that we're transporting heat around crucially relies on the fact that there is this internal mixing within the ocean driving mixing of transport of heat vertically as well as polewards. And understanding that process is extremely difficult. And the reason really that it's extremely difficult is the turbulence happens on very small scales and has very large scale effects. And when you have small scales that you've got to describe that have an effect on very large scales, it proves extremely complicated to understand. Now, for example, one of the things in the policy that we're concerned about, of course, is sea level change, which could be associated with the fact that the ocean is heating up, so that it expands, associated with melting ice that is on land, like on Greenland or on the continent of Antarctic. That if that water ends up in the oceans, it will cause sea level rise. And we have a record measured by sailors dating back 200 years, and it has got more and more accurate as we've measured things, with the satellite altimetry data and so on. We can measure things quite accurately, and we've seen how the sea level is rising. It's really quite accurate now. But the real question for people living in the Netherlands or whatever is what's going to happen in the future. And there's a wide range of uncertainty about that. And it's in the news a lot about how much the ice sheets will melt. That's one of the big areas of great uncertainty. A second area of uncertainty, which is also more frequently in the news, I guess, because of extreme weather events and so on, is how clouds are formed and the effect the clouds have on the climate. Because you could imagine that clouds can both act to increase the greenhouse effect, that they will act as a blanket, but also they're typically white, and so they may reflect heat back. So there's a lot of uncertainty about clouds, and it's very, very hard to model them. But there is another area of uncertainty, which is the area I'm particularly interested in, which is the internal wave dynamics and the internal wave mixing within the oceans, which is leading to this columnar mixing that I was describing. Now, we're all used to waves. Here's a picture of a duck on the cam setting off these surface waves, and you understand how waves work, of course. You perturb the surface, you lift the water up, it feels a gravitational force wanting to push it down, it goes down, and just like a kid on a swing, when it goes down to its equilibrium position, it now has a velocity, so it keeps going, and so you have an oscillation occurring, you get a wave. And that's what we're used to seeing at the surface. Here's a picture of the Atlantic. This is off Malin Head, the northernmost point of Ireland, where the Millennium Falcon lands in the Last Jedi, and you see these surface waves. But I am talking about internal waves, because since the ocean is stratified, the wave mechanism is you lift water up, water is more dense than air, so it falls back down. But if you have a water column and it's more dense near the bottom and less dense higher up, and you lift the dense parcel up, that also sets up a wave field. And understanding those waves is the fundamental question, and how those waves drive mixing when they break, because there's clearly mixing here between the air and the water, the whitecaps. That's one kind of mixing. That's also very important and very hard to understand for the global climate. But I'm talking about mixing, hidden mixing that's happening inside the ocean that you can't necessarily see. And that's what we have been working on for decades. And we're still arguing we don't really know the answer. So here's a little bit of maths about this particular phenomenon. So look at the picture in the top right-hand corner. If you lift a parcel of fluid up some distance, zeta, and it is then dense compared to the environment, just like a lead balloon would, it'll want to fall down. But as it falls down, it falls back to its equilibrium position and overshoots its equilibrium position and goes down. So you end up with this oscillation. And you can describe this mathematically. You can look at the force that the blob of fluid would feel if it was lifted up some distance. And that is dependent on the density gradient you have in the environment. And following our good old homeboy Newton, of course, the force is the mass by the acceleration, but the acceleration, of course, is the second time derivative of the location, with the second time derivative of the location of this blob of fluid. And so I end up with a second order differential equation of simple harmonic motion, where notice if the density gradient is decreasing with height, this then works out to be positive, defining therefore a frequency, which we call the buoyancy frequency, which is the frequency this blob of fluid would oscillate through, going up and down. And it doesn't just have to be a blob, it could be an entire column of fluid going up and down, up and down. And so Just like the surface waves go up and down, this is internal to the water goes up and down. But then you might think, and this is the really curious things, what happens if I force the fluid at some frequency that is different from this natural frequency? And then something really peculiar happens, because that is, if the frequency of forcing is lower than the frequency of the natural oscillation, that is equivalent to not moving the slab up and down vertically, but moving it at an angle, because then you're reducing the effective value of the frequency by tilting the angle a little bit. And so here is a video from Barry Ruddick showing this very phenomenon. What you're looking at is something called a Schlieren picture. And really what it does is it shows gradients in density. So you can detect when dense parcels are moving up or light parcels are moving down. And so this is a bar that is holding a cylinder that is pointing into the board. And when we start to move it, we see these waves. And these waves behave in a really interesting fashion. Remember, we started forcing it at this point here. And so therefore, from causality, from information, the information about that has got to go away from that point. But if you look at the individual wave crests, follow this red bar or this blue bar, they appear to be going downwards. They're going orthogonal to the wave energy is going that way, but the wave crests are going this way. They're really freaky waves. And you'll see they go at a given angle, and that angle is determined by the frequency at which they're being forced. It's this thing about moving the slabs diagonally. The ocean is full of waves like this. It is just a zoo, a soup of waves flying around. And sometimes these waves interact with other things and break and mix and deposit their energy, and understanding how they deposit their energy is the thing I am obsessed with. And I have convinced other people to study a lot. So here's a beautiful schematic picture due to Jen McKinnon, who's an oceanographer at Scripps Institution of Oceanography in San Diego, showing they did this large study called the Climate Process Team. They did this large study to try and understand the influence of internal waves on the dynamics of heat transport in the ocean. And there's a whole load of things, different processes that can happen. There's tides in the oceans, of course, flow going backwards and forwards. And so if the tides go over rough topography, you lift dense parcels up, go down, you can emit waves from those. Remember, these waves propagate at a given angle for a given frequency. So when they hit sloping boundaries, they can then deposit their energy because they can't reflect. These aren't like waves about that the angle of reflection is the same as the angle of incidence. The angle of propagation is set by the ambient. So these waves can come in, they'd want to reflect at a given angle, and if that angle is the same as the slope, boom, they break on the slope. If they flow over mountains, there's a current flowing over a mountain, you have something called a lee wave. You eject the waves in the lee of the mountain, get sent up. These are observed in the atmosphere too. And then waves can interact with currents, wave-wave interactions. They can be forced by storms at the surface. The thing to remember is the ocean is full of waves, waves break, and so what is the energetic effect? Because when you break, you might mix the fluid up, and therefore you're transporting heat. And this picture has this perfect periodic box, which is what a mathematician likes the look of, right? Because it's very, very complicated to model the real oceans, but can we look at some idealized cases that still give us some insight? And so that is what I have wanted to do. We've been trying to understand very idealized cases that still have some components of the world's ocean to understand what's happened. And so here's pictures, the fundamental question, and 3 of the pictures of the students. And I just think, so this is Rosie Oglethorpe, this is Kanwar Nain Singh, and this is Chris Howland. And the photographs are taken, this was right at the very beginning of Rosie's thesis. This was while Kanwar was still doing his experiments, because in our maths department, we actually have an experimental laboratory. And this is the moment Chris submitted his thesis, and he's somewhat more relaxed in that image. But what we want to understand is is heat transported effectively vertically in the oceans? And really by breaking waves. And that really reduces to a mathematical question to try and work out what's called the Eddy diffusivity of heat. What you're really trying to do is to say, okay, just like if I heat one end of a bar and keep the other end cold, the heat will diffuse down it. Can the process of turbulence act as a quasi-diffusive process that will mean that the heat will transport along? And so the example here is, suppose I have some stratification represented by this blue line. It's more dense near the bottom, less dense higher up. And I have some turbulence, which I show by those sort of red eddies. What's that going to do to the stratification? Is it going to make the middle layer completely well mixed? Is it going to make it not mixed at all? Or is it going to do something in between? And if we look at the fundamental equation relating the kinetic energy of the fluid to various other quantities, this can be very reasonably thought of as the taxation rate of turbulence by stratification. Because turbulence usually acts that when you cycle your bike, for example, you're putting in energy, the power by cycling your bike, and the turbulent drag you're experiencing, the wind blowing behind you, is dissipating that energy. And so if there isn't stratification, that's the exchange. Forcing goes to dissipation. But there's an extra taxation if you have stratification, because this thing here has got this profile, the solid blue line profile, has got a higher potential energy than the dashed line. And so stratification also can convert eventually, it's a very simplified picture I'm describing, kinetic energy can go to viscous dissipation, or it can go to increasing the potential energy. And understanding how much of turbulence in a stratified flow goes into viscous dissipation, and how much goes into potential energy, caught by this flux coefficient. This is the rate at which the potential energy is increasing. This is the rate of viscous dissipation. The real question is, what's gamma? And that goes into the large-scale models that do for us to help the policymakers understand how the climate is evolving. And these two pictures I've got here, the one on the left is from Chris's thesis. It's a numerical simulation. The one on the right is data from a laboratory experiment, is trying to show us, this was a picture of how the dissipation varies in a stratified flow with waves and shear and all the sort of things that might be relevant to the ocean. And this being an experiment is an image of a stacked image, I'll try and describe it in a minute, of how the density field is varying in a long-term experiment. And you see that sometimes there are sharp interfaces, sometimes there aren't any sharp interfaces, things are mixed. If you look closely, you'll see there are things going at a diagonal which are associated with wave propagation. And over here in the greeny video, the numerical simulation, you certainly see things that might be like waves, but you also, if you saw that, you might just in common language describe that as turbulent, right? And so why is it turbulent at the top and the bottom of the domain, but why is it really quite quiet in between? These are the sort of questions we ask, always trying to understand how does the mixing, how can we model the mixing, the partitioning between energy injection through the waves or the tides or large-scale currents, heating, and how does that go into mixing to transport heat vertically in the ocean, and how does it go into viscous dissipation, so it's kind of lost from the system. And these are the questions that we are really trying to understand, and we use three different things. We use we use maths all the time, of course, but we use numerical simulations, we use laboratory experiments, and as I'll say, we also use real data measured from the world's oceans. So, what do people know? It's really the most important thing to take away. There are two things I want you to take away from this talk. One, that the ocean is full of internal waves. And then the second thing is, the way those internal waves transport heat and momentum is still highly controversial. It's really not very well understood. Many people all over the world are working on it, but it's really not very well understood. This is a summary state of the knowledge from a review article about 12 years ago from a group largely based in Stanford. And they were saying that the mixing efficiency, which is related to this gamma, when a parameter is small or when it's large, this quantity appears to go to zero, but the standard model that is said that it's about 0.2, which is what's used in the numerical models, this limit doesn't appear to be justified. And this is not simply a matter of curiosity. And so the real question is, how is this mixing, this flux coefficient, this taxation rate, How does it depend on parameters? Because that's what you'd always want to say. If something goes up, something else goes up. You know, it's like you can think of it, you know, the state of the economy depends on the unemployment rate, depends on the interest rate, you know. So the output that you're interested in, the taxation rate, how does it depend on other parameters? And it could depend on the properties of the fluid, the viscosity of the fluid, the thermal diffusivity, the way that even if the fluid wasn't moving, how heat would diffuse in it. It could depend on this buoyancy frequency. It could also depend on shear, the way velocity varies with distance, because that seems to be a natural way that waves will break. If you have fluid going faster here and slower there, the shear is something that injects energy and it could cause mixing. It could be properties of the turbulence. It could be how strong the dissipation rate is, epsilon, compared to how big how energetic the flow is at the particular moment, how big the kinetic energy is. It could be some combination of these, which is this REB quantity. How does it depend on these parameters? That's really the question we're trying to answer, though I warn you, we're not going to have a definitive answer in the next 10, 15 minutes. So 10 years later, a different group at Washington, led by Mike Gregg, a lot of oceanographers involved in it, say it's long been understood that the mixing efficiency is not a constant. It may depend on other parameters. However, the data, measurements from tracers and microstructures, appears to agree better with saying that it's a constant than not saying it's a constant. So 12 years ago, people were saying, you know, the data, experimental numerical data really seems to say that it strongly depends on this, on parameters, which seems reasonable. And then, yes, but if you suppose it doesn't vary with parameters, you actually seem to have a good agreement with real observations. And so it's really, really unclear what the answer is. And so I've been, with many other people, have been interested in trying to understand idealized cases to see if there are situations where the parameter is constant, or does it depend on parameters? With the quantity of interest, the mixing coefficient, does it depend on other aspects of the flow that could be, that we could say, okay, we're looking at this kind of flow, it behaves in this kind of way. We're looking at that kind of flow, it behaves in that kind of way, you know, kind of getting a lookup table, you know, stereotypes of different behaviors. Or should we just say it's a constant and just not worry? Or is there something in between? And really that's what we've been interested in. So to get back to that, the experimental picture that Kanwar and Rosie were working on, they were looking at this flow, which is called a Taylor-Couette flow. G.I. Taylor was a great fluid dynamicist of the 20th century. And what it is you have two cylinders. You have an inner cylinder and an outer cylinder, and you fill it with salty water. And you have salty water, more salty at the bottom, fresh water at the top. There's a trick about how you can do this. And then you spin the inner cylinder, which introduces a horizontal shear. And so you have the water near the inner cylinder is moving fast, the water outside is moving slow, and so you can inject energy, and then the question is what happens? Something very strange happens. Now I'm going to run the video on the left first, and then the video on the right is like a long biotapestry of stacked together images from the video on the left, where we've taken the line of pixels directly perpendicular to the tank, and put one at one time, then one at another time, then another time, stack them up, and then cut to make a long, long tapestry, and then kind of pan the camera past them so we can see how that line goes. Now, since this is salty water, we know that, and we know with this, the refractive index of light through it changes depending on the density of the fluid. And so you can detect structures because if there is a strong change in the density, light is bent. So in particular, if you have a sharp interface, a region over which the density changes rapidly, some of the light will be refracted. So you'll see a black line and a darkening and then a brightening. And so I'm going to run this experiment. It looks a bit wobbly at the beginning. You're spinning the inner cylinder and look, it spontaneously forms these interfaces. You see sharp lines of black and white, which shows that there is a strong gradient in density. And then you have sort of granular regions, which are regions where it's mixed. But if you then look really closely, you'll see patches where the lines appear, then disappear, then appear, then disappear. And so when you do the biotapestry, you see, remember this is the line just taken from the center of that cylinder, you see these regions where there is an interface, and then the interface disappears, and there is an interface, and the interface disappears. The disappears is something's mixing. There's a turbulent event, and then it dies away, turbulent event, dies away. You see these spiral, clearly wave dynamics are going on from the top and the bottom. And you see these very, very clear periods. You know, once again, waves are associated with clear periods. You see there is a line, there isn't a line, there's a line, there isn't a line, and there's a coupling from top to bottom. But if you run a probe, that's what you can see in at the right-hand side of the left video. It's measuring the conductivity of the water, which then tells us the density of the water. And so therefore that tells us how much salt is being transferred vertically. And we're able to then calculate that flux, and we find a really universal property. It follows this particular curve, which tells us how this mixing depends on parameters. So from an experiment like this, we're able to identify the dependence of the mixing on various parameters. Though unfortunately, it's a bit controversial about whether the data is actually decaying as you go to very strong stratification, or is tending towards a constant as you go towards strong stratification. It's sort of uncertain. And going towards a constant value for strong stratification suggests that you can have mixing in the ocean at all times, which is of very great interest. So can we look at the numerical simulations to try and understand that? So here, what we did was we had internal waves bouncing around in the flow. And we also put a large-scale shear, and we also put in a forcing. We kept forcing the flow so that the turbulence didn't kill it. And we saw a very, very strong, amazing correlation between the flux, the mixing, and the dissipation rate. Over a very wide range of dissipation rates, either when it is very large or where it's very small, you see they really agreed with each other, which was really surprising to start with at one level, but still it has worked out. And you see over orders of magnitude, when the turbulence is really quite quiet, like in this region, the smooth region, or when it's very strong, when epsilon is large, which is like near the bottom and the top, it's a periodic box, but it's just the way we've drawn it. You see there is a very good correlation that this mixing is about, gamma works out to be about 0.5, very high taxation rate admittedly, but that's what we find. And we're also able to see how it depends on the parameter, this turbulent Froude number, which is really how strong the dissipation of the turbulence is compared to its present value. And it really was independent of that. It's really quite startling how independent it is. It really doesn't vary. Once again, over 2 orders of magnitude, it's a pretty constant thing. But this is a flow where and it is very efficient. It's much bigger than 0.2, which was what the theories had. But it's very big, but it's constant. But this is an artificial flow. We're playing God. We're somehow stirring it, continually putting in energy. So Chris then looked at another problem, which was, let's just have a wave. We're thinking about the sort of situation of a wave meeting a current. So we have a wave field. This is the vorticity, the swirl associated with the wave, but you can just think of it as a wave. You see these sort of tilted lines. A wave, and then it finds a region where the flow velocity is changing with height. And then it hits what's called a critical layer, and it dumps its energy, it breaks, as you will see. Now this is a slice through a very large computational domain. And so the biggest picture is a slice like this. The stratification is pointing upwards, and it's a horizontal, it's a vertical sheet, and the wave is kind of going through it at this angle. And then it is through a box, that is like the end of the box, the thin end of the box, the vertical direction and the horizontal direction. So we have a long, thin rectangular box. And this is a slice through the middle of this domain. I'm going to run this video. This is the vorticity, it's the swirl. And you see the wave goes along and then it breaks. And we have this beautiful picture of the wave breaks. You see these sort of swirling, overturning places. I didn't mention that. There's 2 different kinds of mixing, scouring of very strong stratification, overturning of weaker stratification. And we see this mixing, and this, when it is freely evolving, is much less efficient than the one when we force it. Gamma's only 1/3 rather than 0.4, which is very curious. We don't really know the answer. but we're able to, why that is the case yet, because this is literally fresh off the presses. This is a paper presently under review, just the last thing in his thesis. But it is still very interesting that we're now able to see the process by which a wave breaks computationally. And we can see this breaking mechanism, and that it is dominated, was a topic of controversy, that it's dominated by these sort of overturnings. But if you look here, they also appear to be convective. If you look at the panel on the left, if you look at the right moment, you'll see things that look like mushroom clouds, which is that the wave gets dense fluid over light fluid, and then you get something like a convection dropping downwards. So there we go. That's at the later stages. We've got to come back to watch this convection. So look closely at the left-hand side of the screen. The wave starts to break, and you see these up and down motions. And so there's this really interesting interaction between shear and convection, which we still haven't worked out, but that's why they call it research. So now, this is now the Cambridge consensus. We don't have a football helmet. We have a particular color of our blades. And it's still very hard. Basically, we're saying the present consensus is we don't really know what the answer is. And it really depends on the way the flow is forced. So that picture I showed you, Jen McKinnon's picture of all the different mechanisms. Lee wave mixing is perhaps different from wave-wave interaction mixing, is perhaps different from tidal mixing. And we really need to get to understand all these different diverse forms of mixing to then understand how the flow might actually behave. So that's the kind of nobody knows anything takeaway message. But so far I've talked just about two legs of what we have, ways we can understand stratified mixing. We can do idealized cases in numerical simulations using very large computers. We can do laboratory experiments using very modern data acquisition techniques, doing not only with salt, with heat. We can measure fluid velocity. We can measure things with incredible amounts of data is generated. There's one numerical simulation that I've got that's got 100 billion that I've been involved in. It's 100 billion grid points. At every instant, we have 400 billion different data because we have the three velocity components and the density, and we're interested in hundreds of thousands of those values to get proper statistics. We are drowning in data and trying to understand data. But we also want to understand observational data. So here's a picture of the fourth student I mentioned, Kathy Gunn, who was also sponsored by NOAA, but also supported by the British Antarctic Survey, which also happens to be based in Cambridge. That's her actually on a research vessel in the Southern Ocean, XPT, that is, which measures the density profile in the ocean. But she did a beautiful thesis where she was using the techniques of what's called seismic oceanography to get pictures of the entire water column. And the way seismic oceanography works is that you have a ship and you have an air cannon behind it that fires off a great air bubble which sends sound through the water column. And the speed of sound is a function of the density. So if you have a long streamer behind you with hydrophones and you fire off these cannons sufficiently frequently so that you detect many, many, many passes of the speed of sound through the water with depth, you can then create a picture of how the density varies in the ocean. This is astounding data, I think. Notice that is a picture 140 kilometers long and 2 kilometers deep. And this is an image at 10-meter resolution of what the density field is in the ocean at that particular instant. And with this vast amount of data, we're able to see the difference between the two currents. This was actually off the Falklands or Malvinas, depending on your political background. So there's the Brazil current, this is the Malvinas current, and you see there is a huge difference between their densities and properties, and so we were interested in understanding the mixing and the transport in that. So really, I want to tell you, understanding how heat is transferred in the ocean is crucially important. A big part of how that is done is through internal waves and how they break. How internal waves break is a very complicated problem, and it's very difficult to draw general rules. And you need to understand that we are generating vast amounts of data numerically, vast amounts of data in the laboratory, and vast amounts of data by observation. And taking them all together, you need mathematicians to understand how to extract information from that data. Okay, so that is 40 minutes of me holding forth. Thank you very much for your attention. And now I am flipping over to trying to look at questions. So first question I got is, what kind of real data can you feed into your simulations? So which parameters can be measured in the ocean to quantify internal waves? That's an excellent question. I have got a new PhD student, who's in his first year, called Sam Lewin, we're looking at this very particular question. We are getting very good information about what the density field is, so we can work out what the structure of the buoyancy frequency, the density field at a given instant is. We also can work out what the velocity field is. It's actually now there are direct measurements of both turbulence intensity, small scale structures, and also the large scale currents. And so really what the picture, there's two arguments that two situations we're interested in. We're interested in the situation where what we call an initial value problem, that we have a given flow and we want to know what happens from that initial condition through time. And so that might be that the storm has hit, in that general picture I showed, you could have storms, and the storm would hit and it would set up a forcing in a particular location. What would be the effects of that over time? You can have these sort of episodic effects. But then there's also the question of kind of boundary value problems where you have a continual forcing. And indeed, so there are situations where there is effectively a steady current through a particular place, like there's Samoan Passage is a famous example in the Pacific, that you have effectively a steady flow through some of these lee wave dynamics I'm showing. There can often be bottom currents that go over seamounts and flow relatively steadily. And then you want to understand what when you have a kind of forced flow like that, you'll have a constant injection of energy in a given profile. What steady state does the flow, the jargon, spin up towards? And how does it evolve towards a steady state? So measurements now are of large-scale velocity, large-scale density, and crucially also small-scale structures in them, which kind of tell you how much turbulence is going on. There's very nice work by a former student here, Alexis Kaminsky, who has just been recruited to UC Berkeley. And she did a beautiful study where she was saying, okay, we're all heretofore we've been looking at problems which are kind of quiet. What happens when you have a background turbulence, kind of background noise in the system? How does that modify? And I think that's a really interesting idea that we're just now beginning to get the tools to be able to do. So yeah. First question, I'll tick answer. So this is saying that there are very sensitive dependence to initial conditions. Yes, indeed. There are extremely sensitive dependence to initial conditions in the ocean. I mean, the classic idea of the butterfly effect and the chaos of Ed Lorenz came from trying to model convection in the atmosphere, but very similar problems carry over. We are really fundamentally against the issue that such a complex dynamical system as the world's oceans, which of course, I've made it simple, but they're very strongly affected and deeply coupled with the atmosphere. The forcing about, I've been talking about the buoyancy, but of course a key component of forcing is the wind stress at the upper surface of the ocean, how that wind stress drives currents and so on, and indeed propagates downwards, is a fundamental question. So you really should think of this, well, it's really three phases. There's a coupling between the atmosphere, the ice, and the ocean, and it's a coupled system, very complicated system, very beyond chaotic, really ill-posed. So there's also people who are trying to approach from the stochastic viewpoint, adding inherent noise within the system and drawing conclusions from that. You argue about it. It is still largely classical physics, because you can kind of have an argument of scale separation, that it's dominated by Newtonian kind of with stochastic effects, but it is dominated by Newtonian rules. The quantum realm does not affect us directly, though certainly uncertainty concepts are definitely highly valid for what we're interested in. So I'll say I answered that one. Oceans are stratified by both heat and salt. This brings double diffusive processes, which also increase vertical mixing. How important do you think it might be to include those processes? Right, well, yes, I've got an informed audience, that's great. Most definitely, double diffusive effects are critically important, and they're important in different, there are different regions of the ocean where they are important. So double diffusion. heat and salt diffuse at very, very different rates. So salt is diffuses much more slower, 3 orders of magnitude slower than heat does. And this leads to some very, very interesting dynamics, which is this double diffusive effect. So for example, think if you're in a situation where you have hot, hot, salty water over fresh, colder water. And this can often happen in situations where there's high evaporation, the Mediterranean perhaps. So if you have, now imagine do this sort of thought experiment about a blob of fluid. You move that hot, salty blob of fluid down a bit. Now, it's hot and salty compared to its environment. Now the heat can diffuse out very quickly because it's cold around. The heat diffuses away. And so it's now kind of as cold as the environment, but now saltier than it. So it's now more dense. So it'll keep falling. So even though to start with, the hot, salty stuff might be less dense, you make something hotter, once you're far away from 4 degrees, you make it hotter, it becomes less dense. You make it saltier, it becomes more dense. So it could be the heat wins and the hot, salty stuff at the top is less dense. But if you move it down and the heat diffuses out, it becomes more dense and it can run away and so drive convection. Now that's the kind of regions where there's high evaporation. But there's also the case near the poles where you can have cold fresh water because and you can that's entirely possible, and you can have a very similar phenomenon can happen. There's 2 kinds. One leads to fingering, the other leads to a diffusive process. Now, this is very important in some parts of the ocean, and indeed often, as the examples I'm describing, very much can be associated with regions that are kind of close to the surface. It is a controversy how important the double diffusive transport effects are compared to these hydrodynamic effects that I'm talking about, which are really associated with breaking waves. And really, when I did that schematic picture and I talking about the periodic box, I should have made the point, I'm talking about a periodic box at the interior of the ocean. So a long way away from boundaries. And so there, to suppose that the dominant process is due to a single stratifying agent like heat is more applicable. Because there's even further weird phenomena, which is called the thermobaric or cabling, which is, I've ignored the whole effect of pressure because we kind of think in our day-to-day life, water is an incompressible fluid, gases are compressible, but water isn't. But there's also the density of water depends on pressure. And so you can be, and because it depends on salinity, temperature, and pressure, you can be in some weird situations that if the water, two pieces of water, with different amount of salt and heat in the 2 of them, that if they're this height, at this pressure, this parcel here is less dense than that one. But if I increase the pressure, let's say by a wave going round, so they go down a bit, it can happen that when they go down, imagine a periodic box, they've gone down, now the parcel on the top, because of the relationship between pressure, temperature, salinity, and density, it can happen that the top parcel is now more dense than the bottom parcel. And so you can get a convective process out of that too. It's called cabling. Really, the ocean's weird. And there are and understanding these processes is essential to getting good models for how oceans work. So, is there a role for machine learning in the data analysis? Most definitely there is. A postdoc has just started with me, one of my colleagues here, Rich Kurzweil, and also with Matthew Alford, who I mentioned at the beginning. He's another observational oceanographer at Scripps in UC San Diego. And that's precisely what we're doing. We're saying, let's look at the data and use machine learning to try and extract other information from the data. And there are also several groups, the next generations of climate models are really using, several groups across the world. NYU, there's a very strong group called the GFD, the Geophysical Fluid Dynamics Lab at Princeton. They're also looking at using machine learning. Caltech are doing this, Imperial College. I know there are groups all over the place saying, look, we have all this data, and we have analyzed them in a traditional fashion, let's try and use the concepts of machine learning with physical insight. We've got to supervise what we're doing to physical insight to improve our parameterizations of these mixing processes. Oh, can you explain how sensitive global ocean temperature is to changes in gamma? How much difference is 0.2 versus, that's a very good question, right? So this taxation rate, so it's saying you have a given, that 20% of the energy would go into vertical transport of the stratification as opposed to 40%. That means you would be transporting twice as much heat vertically as heretofore. And one of the problems with that is, there was a given, the leading order why that matters is it's not just heat that's moving around that we're interested in. It's also other things like carbon dioxide, because of course those waves that break at the surface, those little bubbles mean that you get air and the air goes into the water and some of the carbon dioxide dissolves in. You know, acidification is an issue. And other scalars like iron, like other nutrients like the phytoplankton, all these things, the rate at which they're vertically transported is critically important. So if heat is moving twice as fast as you think it is, that is massively changing what you are inferring as the circulation rate for the water. And if it's changing what you're inferring as the circulation rate for the water, all these other things that are along for the ride with the heat are going up and down the water column much faster than you think they are. And so that is deeply important to understand how stuff gets into the deep ocean. I'm mixing my use of the word deep. The wind blows at the surface. So you typically have, and induces turbulence there. So you typically have a mixed layer near the top. And then you have something called the thermocline, because you have a strong gradient in temperature, or picnicline, because you have a strong gradient density, which is 100 meters or so. Remember, I'm saying the ocean's 5 kilometers deep, and I'm interested in mixing processes that are happening at 2 kilometers down. So and also remember the heat, 3.4 meters is the same as the whole atmosphere. So if the depth of the mixed layers changes, or the transport out of the mixed layer of other nutrients, of other scalars like carbon dioxide, into the deep ocean is different from what we think it is, or what we're modeling it is, the residence time of things and such like the overturning time is going to be vastly off, which then will tell us, you know, that scary plot I showed you at the beginning of The Guardian, of the zetajoules of heat going into the ocean, it is terrible and very, very deeply worrying. The question is, if that is all heating up at the surface, the ice cap's going to melt, the climate, the weather patterns, which are, you know, hurricanes and typhoons, and the monsoon is very much driven by what's happening at the bottom boundary condition, i.e. the top of the ocean. But if what actually happens is you get a lot of heat much deeper in the ocean, we've got much more time to deal with decarbonization. That's what the real prize is in this situation. What are typical frequencies for these internal waves? Well, their periods of oscillations are of the order of minutes. But though they can get all the way towards, I've been interested in the relatively small waves. I have ignored the effect of rotation. When you start getting to periods of the order of the day, you then go from not from just internal waves, internal gravity waves like I've been describing, you get inertial gravity waves, inertia gravity waves, because they then know about the rotation. And the effect of rotation also has a restoring force that leads to waves, because you know, kind of think of it, you can just think of it in terms of angular momentum. You push something out, it wants to come in. You know this from being on roundabouts. You push it, there's a restoring force associated with that, which means that you get waves that are due to the very presence of the fact that the system is rotating. What practical applications do you foresee in the work that you're doing? Saving the planet. So the understanding how density interacts with turbulence is very, very common in many industrial processes. And indeed, in so for example, most foodstuffs, the mixing tanks end up being stratified. The density variations within them. Understanding stratified turbulence is also something, my other line of interest in particular is looking at building ventilation. And decarbonizing the built environment, you know, is one of the biggest, it's a bigger contributor. I think it's the same order as contributor as transport. Everybody's worried about cars, but actually the heating and cooling of housing is a really critical challenge to reduce, the British government, from 2025, you won't be able to have a gas boiler installed in a house. What's that about? That means because we want to change the way we heat and cool our spaces. If we can reduce the energy demand for heating and cooling our spaces, we can then reduce the energy impact. How do you do that? Well, I'm talking a lot. The hot air is rising. There is an interaction between heat and fluids and stratification in all built environments. You know this from, if you've ever changed a light bulb, it's typically hotter near the ceiling than it is lower down. And so the interaction between turbulence, fluid flow, and density variations is critical for many industrial processes, but also for air movement in the built environment. And indeed, I am not involved in it, the colleagues are involved in it. Understanding droplet dispersal is in a stratified environment, like can occur, for example, in a hospital ward, is clearly deeply important in the COVID crisis. Yes, AI is another question about AI. AI can use finite elements analysis, the kind they use in engineering. Look, I didn't get into the nitty-gritties of the numerics of what I was doing. So the particular numerical simulation I showed used an algorithm called pseudo-spectral. It was based on Fourier decomposition. But another research group, particularly the group in Canada and now in Woods Hole Oceanographic Institution on the east coast of the United States, they do use indeed a finite element code. Yes, it's a computational tool that we use. How much mixing is there between deep ocean and the surface? Events important? Yes, so there is if I was doing a course on the dynamics of the ocean, there is another key process that happens, which is we have the crust, the tectonic plates, and as the crust moves apart, at the deep ocean, like along the ridge, the mid-Atlantic ridge, there are vents, and those hydrothermal vents pumping out stuff, you see them with these deep sea submersibles, they are actually injecting a non-trivial amount of heat into the ocean. It's not as big as the thermal heat forcing from the top, but it is a non-trivial amount that needs to be taken into account if we're actually trying to compare the models that we are, the modification of the models we're doing for how heat would be transported vertically due to breaking waves compared to observations. And so I was involved in a project where we were having to include that component for an argument that our model was a bit better than previous models because you need to worry about it. It's a non-trivial component, the heat that is actually coming from the inside of the Earth into the bottom of the ocean. Now, it is very controversial about what the residence time, how long it takes for an individual fluid parcel to get from the very bottom of the ocean to the top and back again. We have some very good data effectively as a byproduct of the nuclear testing that tells us how this has happened, because the radioactivity has changed discontinuously when people were testing nuclear bombs in the air. But it's still quite controversial about for individual lifetime, what the distribution of lifetimes of parcels that circulate in these currents, and indeed it may depend on different basins. So are there compounding or feedback effects with mixing? i.e. mixing may affect one of the parameters, which, yes. There are profoundly confounding effects, and these are very controversial. Indeed, there is courteous debate at the moment about whether some of these parameters are highly correlated. I wrote down a set of 4, but there's a very strong argument that some of them can be quite strongly correlated, that when one goes up, the other goes down. Indeed, there is an argument that there's something called the strongly stratified turbulence or layered anisotropic stratified turbulence regime, which is characterized by being very turbulent, but also being extremely strongly stratified in a mathematical sense. And I am of the opinion that that isn't possible. I think you spontaneously get a layering phenomenon, that you have a region where the stratification is weak beside a sharp interface. And that's that is generic in the mathematical jargon. But there's a lot of debate about whether these things are correlated, and it's really greatly argued. So the turbulence is profound. Somebody else has asked about, is this turbulence isotropic? Sometimes it is, sometimes it isn't. It depends on the scale. And indeed, a lot of the evidence is that much of the ocean is profoundly anisotropic, because we have introduced always the anisotropy of the fact that there's a gravitational field, and so the vertical direction is different from the other two if the fluid is density varied, and there's typically always some density variations. On very small scales, it can end up isotropic, so you actually have a hierarchy of scale, a range of scales, and there's something called the Osmodov scale after a Russian scientist, and if you are below the Osmodov scale, there is an argument that the flow can be isotropic. And so the question is, how big can an Osmodov scale be to allow us to have isotropic turbulence, i.e. turbulence that doesn't depend on the direction? Okay, well, I think I'm out of time, and I've still got several questions. So I think what I will say is that thank you very much for your attention. Please enjoy the rest of the festival, and I think, I don't know if I didn't appreciate if I could still manage to answer, but if I can still manage to answer, I will type answers to the remaining questions. So thank you very much for your time.